How is it even possible to build something as ridiculously complex as a computer from scratch? Well, it's not magic. It's actually a kind of mental superpower that every great engineer uses. And today, we're going to unlock that power by breaking down two core principles: abstraction and implementation.
Okay, so let's really dig into this. How do you build a modern computer, starting from, like, absolute zero? I mean, just picture it for a second. The sheer number of wires, chips, all those components. The task just seems, well, monumental. Almost impossible, right?
And that is the challenge. If you look at a computer's architecture, it's just this dense, tangled web of interconnected parts, and every single piece has to communicate perfectly with every other piece. The complexity is it's staggering. So where do you even begin?
Well, here's the thing. There's a secret to it. It's this incredibly powerful engineering mindset that lets us just slice right through all that complexity. It lets us conquer the challenge and build the entire thing one logical layer at a time. It's not magic, folks. It's a method.
So at its heart, this method relies on two principles. They're actually pretty simple, but they're also incredibly profound, and they work together perfectly. They are abstraction and implementation. And trust me, mastering these two concepts is the key to tackling pretty much any large-scale project.
Okay, here's the entire philosophy in a nutshell. It's all about separating the what from the how. We're going to focus only on what a component does, its function, and we're going to completely, and I mean intentionally, ignore how it actually does it. That mental discipline, that's the whole secret right there.
All right, let's start with that first principle, abstraction. Let's see how this helps us build our understanding of the whole system. Because this is where we define the rules of the game for every single component.
So, in computer science, abstraction is really just a promise. It's the set of operations or services that a component guarantees it will provide. A great way to think about it is like a contract. It tells you exactly what you can do with this thing, but it reveals absolutely nothing about all the complex machinery working away on the inside.
A car's steering wheel is the perfect real-world example. Its abstraction is super simple, right? You turn the wheel left, the car turns left. As the driver, that is literally all you need to know. You don't have to understand the intricate mechanics, the steering column, the power hydraulics. Nope, you just trust the abstraction. Okay, so how do we apply this to building our computer? Well, the strategy is to start at the highest, most complex level, the computer itself, and then we start breaking it down layer by layer. We define each major component as its own simple, abstract building block.
So we start by treating the entire computer as one big high-level component. Now, its implementation is just a collection of simpler parts, right? Things like RAM for memory, a CPU for the brain, an ALU for doing math, and for now, we do not care one bit how the RAM works. We're just using it as an abstract part.
And this is the beautiful, simple abstraction of a RAM unit. This one little sentence is its entire contract. As someone who's using the RAM, this is all you have to know. Give it an address, and it will give you back a value. That's it. It's like a magical library with billions of books, and all you have to do is shout a title, and that book instantly appears in your hands.
So, if you're the person building the main computer board, the RAM unit is just a complete black box. You don't need to know how it does its little hocus-pocus inside. You just have to trust its abstraction. You trust that it's going to honor its contract, take an address, return a value. Simple as that. But of course, at some point, the magic has to stop, right? Somebody, somewhere, actually has to build that memory unit. That hocus-pocus has to be implemented, so how does it do its magic?
And this is the crucial insight. This is the really cool part. We just repeat the exact same process. We switch hats. The RAM is now our new high-level component, and we find out that it's built from even simpler parts, little things called registers to hold data and logic gates to make simple decisions. See what we did? We just peeled back another layer of the abstraction.
This repeating recursive pattern, this is what makes the impossible possible. To build the RAM, we use registers, but again, we only care about what a register does, not how it's built. And by focusing on just one single layer at a time, we stop the overall complexity from ever overwhelming us. It's brilliant. Okay, but this brings up a really important question, right? Who is the person that decides how to break this massive problem down into these neat, elegant layers in the first place? I mean, who designs these abstractions? Well, that is the absolutely crucial role of the system architect. They are the mastermind who looks at a giant problem like build a computer and strategically carves it up into smaller, independent, and most importantly, solvable pieces.
A great architect doesn't just manage complexity, they literally design it out of the system from the very beginning.
So, the architect is the one who delivers the blueprint. For every single component, they define its interface. That's the what we talked about. And this part is so important, they also provide a test plan. Now, why is that key? Because it means a team can go off and build and test their one little piece in complete isolation, totally confident that it's going to plug into the larger system perfectly later on.
Okay, let's zoom back out for a second, because I want you to really appreciate the ultimate power of this approach. This isn't just about building computers, it's about building anything complex.
This right here is the big takeaway. The ability to think in these modular, abstract layers is, you could argue, the single most important skill in engineering. And why is that? Because it allows huge teams of people to work in parallel. Each team can just focus on building their own black box, trusting that as long as it honors its contract, the entire system will come together and work perfectly.
So, I'm going to leave you with this final thought. This superpower isn't just for building computers or hardware. It's a way of thinking. It's a tool for breaking down any overwhelming challenge into manageable parts. So the real question is for you, what complex problems in your own life, maybe at work or on a personal project, could you start solving today, just by applying this powerful principle of abstraction?